In this video, I'll be helping you with the ALEKS problem type called graphing an ellipse given its equation in general form. And again here, instead of jumping into this example, we'll first take a short detour to talk about the standard form of an ellipse and then come back to this example. All right, this is a short sidebar to talk about the parts of an ellipse that you're going to be asked to calculate. And before we look at an ellipse, I would like to start with a circle and then see how that turns into an ellipse. We have the standard form here for our formula of a circle, x minus h squared plus y minus k squared equals r squared, where hk represents the center of a circle, and the r that's being squared is the radius from that center. An ellipse is similar to a circle, except that it appears to be stretched. And from the standard form of an ellipse, we can see that it still has that center, hk. However, the stretching occurs as a result of being divided by a squared, which gives us the length from the center out to the ellipse, which we can see here as a, the square root of a squared, and b squared, which is similar, but the distance from the center in the other direction is b. But notice it's still addition, and that where we did have the radius squared, an ellipse will always be 1. I would also point out that the a and b are always chosen such that a is greater than b. And you can see in this example that the a squared is under the x term, so it has been stretched horizontally. If the a squared was under the y term, then the ellipse would be being stretched vertically instead of horizontally. But for this example, I'll keep it horizontal where the a term is under the x value. For terminology, a is the major axis, so the length of the major axis is 2a, and b is the minor axis, which has a length 2b. Along the major axis, we also have the foci, which is the point c, where c squared is equal to a squared minus b squared. And this is important because C defines the ellipse, since any point on the ellipse has a distance to the foci and a distance to the center. The sum of these two distances for any point is always the same. Okay, with that information about the standard form in mind, I've got one possibility written here for a standard form. The other possibility is that the a squareds and b squareds could be switched. But the first thing we're going to have to do is take this ellipse in general form and write it in this standard form. So I'll start with what's given. And looking at the standard form here, I can see that on the left-hand side, I want these perfect square terms. And on the right-hand side, I want a single 1. So I'll start looking at that x squared. Since there are no other x's, that really is already a perfect square. But for the y's, we will need to complete the square. And I'll start by factoring out that common 16 from both of those terms, leaving me with y squared plus 4y. I'll leave some room to complete the square. This 48, since there are no other constants on the left-hand side, I'll go ahead and subtract that over to the right. So a minus 48 on the right-hand side. From here, I can complete the square inside this parentheses by taking half of the middle term, which is 2, and then squaring it would give me a plus 4. But since I just introduced this plus 4, on the left-hand side, I've actually just added 64 because that 16 would be distributed to that 4. So if I add 64 to the left-hand side, I must also add 64 to the right-hand side. Rewriting this, I now have x squared plus 16 times, we've created a perfect square here. This is y plus 2 squared equals negative 48 plus 64 is a 16. We've gotten much closer to standard form, but I need to get rid of this 16 coefficient in front of the y squared term, and I need the right-hand side to be 1. So this works out perfect if I divide both sides and each term on both sides by 16, I would then have x squared over 16 plus y plus 2 squared. These 16s cancel, so my denominator is just 1, and that right-hand side is now 1. So we can see that we now have standard form, and I can begin to graph this because my h and k, since there's nothing being subtracted from the x, my h term is 0, and my k term, this is y minus k, my k is negative 2. So our center is at 0, negative 2, and then a squared, which is the larger of the two denominators, is 16. So a is 4. And since that is underneath the x term, I would go horizontally 4 units to the right of the center and 4 units to the left of the center. This would be my major axis. And then b squared is 1. So b is 1. That's underneath the y term. So I would go up 1 unit and down 1 unit from the center. So these 4 points I can now connect to graph this ellipse.